Okay, so next we'll have Stephen Bocquet, who will be talking about galaxy cluster cosmology with the South Pole telescope.
All right. Can you hear me? Does that work? You can hear me, but you know. Okay. Someone in the back says that yes. Okay, cool. Then let me get started. Thanks a lot to the organizers for inviting me to give this talk, and thank you all for coming. I'm going to talk about galaxy cluster cosmology with the South Pole telescope. So this is work I did within the SPT collaboration. One member I would especially like to point out is Joe Moore, who's here as well, and who will be giving the next talk. So he's kind of the mastermind pulling strings behind many of these analyses. So you should definitely talk to him as well. These are a couple of the relevant, I think, recent papers about galaxy cluster cosmology with SPT. And I will be going through the details here throughout this talk. All right, does this work? No. Okay, the brief outline of the talk, I'm going to talk about galaxy cluster cosmology in a nutshell, just to get everyone on board. Going to introduce the cluster catalog from the South Pole telescope. Going to discuss our latest and greatest cosmology study, and we're going to conclude with some outlook of what's going to happen in the future. So before I do all that, let me just get all of you on board with this talk by telling you what we will not be doing. So we will not assume hydrostatic equilibrium. We will not assume that we know the hydrostatic bias from some hydro simulation. Please come to talk to me if you want to have a chat about my thoughts on this for the future. What we will do is trust our intuition, and hundreds of papers proving that cluster mass proxies correlate with mass. And finally, that weak lensing measurements of galaxy clusters provide, on average, an unbiased estimate of halo mass. So again, no hydrostatic equilibrium anywhere in this talk. So with that, I hope you're now listening. Let me get to cluster cosmology in a nutshell. As most of you know, if you look at an n-body simulation up here from redshift 4 to redshift 0, you see this cosmic web structure forming, and at the intersection of the cosmic web, you see the nodes that are dark matter halos that will host galaxy clusters. So to do cosmology in principle, it's very simple. You predict the abundance or the number of dark matter halos as a function of redshift, and this will depend on cosmology. So you do that on numerical simulations. So then you get the halo mass function that you've all seen that I've sketched here. So as a function of mass and as a function of redshift, you see that the number of halos evolves. So now you have your model prediction. All you need to do is look at the sky, measure the number of galaxy clusters in your survey, compare the data with a measurement, and you're done. So in practice, however, as you know, this is much more complicated. This is what galaxy clusters look like. So there's no label mass anywhere here. This is from X-ray. These are optical images. We're going to show images from SPT a little bit later. So in practice, what you need to do is an empirical calibration of the mass-observable relation, because you don't observe mass directly. A cartoon I like to show to introduce this concept is this one, where I'm showing a couple different cluster mass proxies. So these are the things we can actually observe. First, let me introduce this plot. You see precision, so basically it's just the measurement uncertainty, and accuracy, that's basically how well do we understand this measurement. So you want to be up here, accurate and precise. You don't want to be down here, and the universe is kind of orthogonal to that, so you got to pick one. And what we're going to focus on in this talk is these two observables, so related to the cluster gas. The only thing you need to keep in mind for now is that they have small measurement uncertainties, but basically they're systematically limited by our lack of understanding of gas physics. On the other hand, we have weak gravitational lensing up here that has a high measurement uncertainty, but we understand very well how it relates to the true cluster mass. So what we will do in practice, and I will discuss this in more detail, is we're going to combine these different measurements to get accuracy and precision. All right, step 2, let me introduce the survey we did with the South Pole telescope and what clusters we got. So one slide about the South Pole Telescope, or SPT. It's a 10-meter diameter telescope at the South Pole. Has roughly 1 to 1.6 arc-minute resolution, so that's very well matched to galaxy clusters. So far, we've installed a couple different cameras. So the first survey that I'm going to discuss in this talk is SPT-SZ. So it observed in 3 bands. The second survey, or second generation of SPT surveys, was SPT Pole. The important update is that this added polarization capability. And now for the third season, we're observing with SPT-3G. So that's just, the next camera, still with polarization. It's much more sensitive, and that's ongoing. So this is the telescope as configured for SPT-SZ. And this is just a nice image showing that it's in the middle of nowhere, close to the South Pole. All right, so how do we find galaxy clusters? It's through the Sunyaev-Zeldovich effect, and we're honored to have Rishi Sunyaev actually here in the audience. So as you probably all know, how this works is that as CMB photons pass through the hot gas of a galaxy cluster, they are upscattered in energy, and then we can detect them with our telescope. So if you look at the right-hand side here, you see in red, that's the CMB spectrum, the black body spectrum, and if you look along the line of sight of a galaxy cluster, you will see the shifted spectrum, which is the blue line here. And if you take the difference, you see the SZ spectrum. And the 3 bands here are roughly where SPT is observing. So this means with SPT, we're basically looking at the decrement of the SZ spectrum. So let me just quickly visualize that. A couple slides just to show off. This is a patch of the sky with Planck. If you look at it with SPT, thanks to the better resolution, you start to see many more features. If you apply the matched filtering, you start to see what I'm getting at. So first of all, these typical ripples here are the primary CMB anisotropies. And the stuff we're going to care about are these dark spots. As I said a second ago, we're looking at the SZ decrement, so clusters will be dark spots in the CMB maps. So just for completeness, the bright spots here are contaminants to us. These are AGN and dusty star-forming galaxies. So very well, with this we've found galaxy clusters. Let's look at the catalog. So this catalog's been out for a while. Black crosses here are the SPT clusters in the SPT-SZ survey, the function of redshift and with mass estimates. And just for comparison, a couple other surveys here. So red points are Planck, blue points are the Rosat X-ray all-sky survey, green is ACT, and this doesn't really do justice to, I don't know where Matt Hilton's sitting. They have a much better catalog by now, but that's status of a couple years ago. One thing I'd like to highlight here is just if you look at this catalog, you see that we have clusters up to very high redshifts. And this is very interesting. I'm not going to go into the details, but to study all kinds of astrophysical effects in galaxy clusters, and just a couple references here of interesting papers we put out. And obviously, you can learn about cosmology, which is what I'm talking about here today. All right, so now let's work our way toward doing cosmology with this sample. Again, this is based on our latest analysis we put on the archive a couple weeks ago. So let me just show you this plot one more time, just as a reminder to be sure we're all on board with what's going on. So what we're going to do is we have the SZ effect that's allowed us to build our cluster catalog, and we have follow-up data with weak lensing measurements and X-ray YX measurements. So for the non-experts, YX is basically the product of X-ray gas mass times X-ray temperature. And this is supposed to be a very precise cluster mass indicator. So precise here again meaning small measurement uncertainty, but big principle, big systematic uncertainty. Now let's look a little bit more into the details of the sample. This is a variation of the plot I just showed you a couple slides ago. Black crosses again are the cluster sample we're going to use in the cosmology analysis. And then highlighted here are the clusters for which we have follow-up measurements in weak lensing and X-ray, as I just discussed. So blue points here are all clusters for which we have X-ray data from Chandra. And then green and orange highlights here are clusters for which we have weak lensing data from either ground-based from Megacam on Magellan or space-based from the Hubble Space Telescope. So if you look at the bottom plot here, that's just a histogram along the redshift direction. Again, you see this very long redshift range for which we have detected galaxy clusters. And then the highlights here again show you that we also have a fairly representative follow-up coverage in the X-ray and weak lensing measurements. All right, so with that, that's basically the data that goes into our analysis. Now let me discuss how we actually use that to learn about cosmology. And again, the important focus is to understand where our information about how mass relates to the observables is coming from. So another cartoon that's hopefully helpful just to get the concept across. Look at kind of the first cosmology in a nutshell overview I gave you. What we're doing is we have a cosmology model that gives us a halo mass function. So again, it's the number of clusters as a function of mass and redshift. So obviously there's two elements. Let's walk down the redshift line. That's trivial in a sense, or solved. So we have photoz's and spex's, and that works. Let's just leave it at that. In the mass direction, what we do is we forward model to the actual observables. And as I introduced earlier, so for the forward model to the SZ effect and X-ray measurement, we know that there are scaling relations, but we don't know their parameters. And finally, we have the mass to the weak lensing shear profile relation, and this one we know. Why do we know this? Well, weak lensing traces all matter, as was discussed yesterday in a nice talk by Suhud. So we can use n-body simulations to tell us how halo mass relates to the weak lensing shear profile, and this is known with percent level accuracy. So basically what we're doing is we use known relation from mass to the weak lensing shear profile to calibrate the mass to the SZ effect and mass to X-ray measurements. And last but not least, we do all this simultaneously in order to account for all observable dependencies with cosmology, and importantly, to capture all covariances between the different observables. All right, one more time, not in a cartoon, but just because this is the most important point, I think. So our modeling framework, again, we say there is a mean scaling relation between the SZ signal and mass that's described by a power law in mass and redshift with a priori unknown parameters. So that's basically where a couple years ago people were still using the assumption of hydrostatic equilibrium. We're not doing that. We have a simulation calibration of the mass to weak lensing shear profile relation. Simulations are needed because halos are not perfect NFW halos, but this is under control. We account for correlated intrinsic scatter among all cluster observables. And then our theory prediction, finally, is the halo mass function as provided by Tinker et al. All right, a couple more words about our weak lensing analysis and our overall systematic error budget. The two numbers I want you to look at here is the total systematic uncertainty we have on our weak lensing mass calibration. So for the ground-based sample, it's about 6%. For the space-based sample, it's about 9%. The important thing, though, is you look at the number of clusters. It's 19 and 13 clusters. So we're actually limited by this low number of clusters for which we have weak lensing data, and we're not yet limited by the systematic uncertainty. So this, I will come back to that. But basically, this means that right now, if you give me more weak lensing data, we immediately gain in terms of constraining power. All right, one slide of math just to describe what we're actually doing in terms of the likelihood analysis. In principle, it's very simple, actually. The top part here is just the log of the Poisson likelihood. So basically, the halos are modeled as being Poisson realizations of the halo mass function. And with a surveyed selection, but in principle, it's really just the log of a Poisson distribution. And then the tricky bit down here is what I call mass calibration. It's basically relating the X-ray YX measurements, the weak lensing tangential shear profiles, to the ESZ observable and redshift. And that's how you get a correct likelihood description of your model. One thing I'd like to highlight is that especially this term here actually looks like that when you write it down. The one thing I want to highlight is you have this quadruple integral that you need to compute in your likelihood. The reason I mention this is that if you want your MCMC chain to run within a finite time, it's actually a little bit tricky to make sure you compute these integrals in an efficient way, because otherwise you just spend months waiting for your results. All right, so once we set this up, let me just show a table that you can't read. The important point is just to tell you what parameters we're fitting for in the end. So up here is the cosmology parameters, basically the standard cosmology models with massive neutrinos and dark energy equation of state parameter. Then you have a bunch of SZ scaling relation parameters, X-ray scaling relation parameters, weak lensing systematics, and correlated scatter among all observables. So this is just to give you a rough idea of the complexity of the problem, I guess. All right, so now let's run all this machinery and let's discuss the results. So first of all, yes?
So I was just wondering, I might have missed this. How do you actually measure the redshift?
Yes, oh, okay, very good question. Yes, we have, so for this exercise, we have targeted optical follow-up and a pretty large fraction, I forgot the number, of spectroscopic measurements, so we can actually calibrate the photo-Zs. The next step, let me just get to that, is we have full overlap with the DS, dark energy survey. So for future surveys, we're actually going to use DS data to do the redshift follow-up. So yes, thanks. Okay, before looking at cosmological constraints, let's just validate that our whole modeling makes sense. So this is one aspect of a goodness of fit test that we say that passed. So what I'm looking at here is the abundance of halos as a function of redshift, or projected along the redshift direction, and on the right-hand side, projected along the detection significance. So that's basically our mass proxy. So you see the best fit model with uncertainties, and you see the histogram, which is the catalog. And the bottom panels here are the residuals, and the dotted points here are the Poisson uncertainty in the survey. So basically you see that none of these residuals seems to be in tension with the Poisson scatter in the survey, so this looks good. Now let's be a little more quantitative. What you want to do in general is something like a chi-squared per degree of freedom. We can't quite do that here because, as I said, we're using a Poisson likelihood. So luckily there's some, basically an equivalent approach to a reduced chi-squared estimate for the Poisson distribution that basically gives you a statistic from your best fit model. So that's 440 plus minus 27. These are just numbers if you want. You compute the same statistic for your data, which is 450. And you see that our data statistic is within the expectation of where it should be. So also this quantitative test also passes. So with this, we have confidence that things hold together. And now let me actually discuss the constraints we got. So first of all, let me just highlight our constraints on X-ray scaling relations we get. So in our analysis setup, we basically get these X-ray scaling relation constraints for free, right? We have the AZ effect to find clusters, we have weak lensing to get us mass information, and we get X-ray basically for free. So why should you as cosmologists care? Well, one important aspect, I think, is that this, for example, could feed back into hydro simulations. We would want hydro simulation to reproduce what we measure. And this could be important, as we discussed yesterday, that if you want to understand the impact of baryonic effects on cosmic shear, for example, you could use this result to validate that your hydro simulations actually reproduce what we observe. So I think there's a really nice complementarity there that we should discuss. Now let me get to the result. Basically here, that's the amplitude of the X-ray scaling relation, evolution with mass, evolution with redshift, and the scatter. And the lines here are the so-called self-similar model prediction. So that's the model prediction if there's no non-thermal pressure support. Interestingly, our redshift evolution is consistent with this simple model. But if you look at the mass evolution, or the posterior here, you see that we're actually in tension with this self-similar expectation. And if you look at the bottom plot here, I'm showing different subsamples. So the full sample is about in 3 sigma tension with a self-similar evolution. But if we only take the low redshift half of our data, which is redshift 0.25 to 0.6, we see very nice agreement. If we take the high redshift half, then the disagreement is even stronger. So currently, that's all we can say. It's definitely interesting, and we're going to follow this up. And as I said, this is relevant because it would feed back into hydro simulations, how they should predict these observables. All right, now cosmology. Let's look at Lambda CDM with massive neutrinos. And let me just describe the money plot here. That's the omega matter sigma 8 plot you all know and love. So blue contours here are the SPT clusters. And then for comparison, it doesn't quite show up nicely here, but gray here is Planck 2015. Then red and orange are cosmic shear, galaxy-galaxy lensing, and galaxy clustering from the dark energy survey and from KIDS plus gamma. And finally, green here is another cluster cosmology analysis using X-ray selected clusters with weak lensing calibration. That's the Mansedal analysis. So the important point is just, they're all kind of on top of each other. There's nothing, crazy here, nothing to be too excited about. But the usual caveat that was mentioned yesterday as well, that it seems like all these low redshift growth of structure probes prefer slightly lower omega matter sigma 8 than Planck, but definitely, in our case, we're in a 1.5 sigma agreement with Planck. So currently, there's not much to be said. Let's see how this evolves. Let's look at our constraint on neutrino masses. As is well known, if you combine a low redshift measurement of sigma 8, for example, from clusters, with Planck, then you break degeneracies in the Planck posterior, and you can, in principle, constrain the sum of neutrino masses. So our result turns out to be actually quite high, depending on what you expected. So we measure something like 0.4 EV plus minus 0.2. So formally, this would be a 2 sigma preference for massive neutrinos, for what it's worth. The important point I want to make here is basically this plot here that's showing the degeneracy between the sum of neutrino masses and the amplitude of a mass observable scaling relation. So the reason this is interesting is, again, we are limited by the amount of weak lensing data in our analysis. So again, if we increase the weak lensing sample, we improve our constraint on this parameter, and we improve our constraint on the sum of neutrino masses. So at least for the next step, it's as simple as that. And finally here, just some robustness tests on the recovered constraint on the sum of neutrino masses, basically playing around with the tau prior, mimicking the Planck 2018 analysis. We see this had a little impact, but nothing dramatic happens. Same thing if we just use the low redshift half of our cluster sample, the posterior shifts a little bit, but nothing significant. All right, now let's switch gears and just briefly discuss constraints on the dark energy equation of state parameter. So from clusters alone, we get minus 1.55 plus minus 0.4. And basically, I encourage you to take a look at the paper and studying all these degeneracies from clusters, Planck, supernovae, and BAO. And I think it's actually quite interesting to understand how they all correlate and how the degeneracies are orthogonal or not. So basically, once you combine all these probes, we get a few % level measurement on W. And the one thing I want to highlight, though, is if you look at the posterior on W here, the interesting thing is that, as was discussed yesterday, if you just look at Planck, you actually see a 2-point-something sigma preference for a lower W than -1. But as soon as you combine Planck with either BAO, supernovae, or clusters, you get something that's centered at -1, which is kind of, maybe surprising or interesting. All right, last result. As was also mentioned yesterday, one way of probing the low redshift or local universe is to measure sigma 8 directly. So we do this measurement measuring sigma 8 as a function of redshift. So the red band here is the 1 sigma allowed region for sigma 8 in a lambda CDM plus neutrino universe taking the Planck parameters. So that's basically an extrapolation from redshift 1100 to redshift around 0. And then the blue crosses here are actually the measurement using our clusters. So you see there's actually quite good agreement. It's a little bit lower, but that's expected given the lambda CDM constraints I showed. Then orange, just for completeness, is the same model with a little more freedom in the mass-observer relation. Nothing too dramatic happens. And green is galaxy density cross-correlated with CMB lensing. All right, and I'm starting to run out of time and coming toward the end of my presentation. Just some outlook of where we're going. As I said, the next important step for SPT is improving the weak lensing. Yeah, I know. Weak lensing mass calibration. As we said, we have overlap with the DES survey, so we will get weak lensing data for all SPT clusters, and this will dramatically improve our constraints. We have SPT Pol, the second generation survey that's finished, and we're about to release the first catalogs, so this will increase our cluster sample. And SPT 3G is ongoing, that will be even deeper and even greater. So let me just stop here. Thanks.
Thank you. Questions?
Thank you. Very nice talk again. So you saw a plot earlier that shows that if you exclude the high-redshift clusters, you get something more consistent. I think it was with a subsimilar model.
Right.
And my question is, a lot of the weight is put on the weak lensing measurements. For the high-redshift clusters, weak lensing measurements are probably worse because you don't have as many background objects. Can you comment on that?
Yes, so I think, well, unfortunately, it's a little bit tricky because currently our weak lensing data really just constrains the amplitude of the scaling relation. And the constraint on the mass evolution we get is basically by fitting for the mass function. Basically, you can assume if you have a model that's like that, and you say, okay, I have my data that's here, and I just know the amplitude, then the fit will make sure you get the right slope. So that's basically what's dominating our constraint on the slope. Meaning that the weak lensing data is not yet able to tell us about the slope directly. And therefore, I think it's unlikely that the weak lensing data is actually the thing that's causing the different slope at low and high redshift. But I think, to be fair, this is kind of our first pass on this. As you say, you just want more weak lensing observations to get the total number of background objects higher, and then hopefully we'll be able to say more about this.
Yeah, coming to your neutrino mass constraint, are you calling it a constraint or is that an upper bound?
Sorry?
Are you calling it a constraint or is that an upper bound?
Well, it's a little...
Because your posterior seems to go down at low neutrino mass.
Well, yeah, I think the paper says something a little more careful. Just saying, if you take basically the mean and the standard deviation and you assume this is a Gaussian, then you get a 2 sigma preference. But obviously, right. it doesn't go to 0. And also, I mean, 2 sigma is nothing.
Right, because would you like to comment on some other upper bounds which you see in literature, which are roughly around 0.12 now, combining Planck, BAO, and Leibniz alpha, I think.
Right. Yeah, definitely if we add these, then the whole thing would shift. So, so I guess, well, the way how we see it is just if we fit this model, we get this. I mean, this, I put this 2 sigma here not to claim a discovery or whatsoever. It's just to say formally, if you assume this is a Gaussian distribution, this is what you get. Now, obviously, you know, what we need to understand is why does this turn out to be so large? But you know, right now, with our analysis setup, this is what we get. That's kind of all I can say, right? But yes, I know that if you do other measurements of it, you actually get a posterior that's here. So that's definitely something interesting that we need to understand.
Not working. Oh, yeah. So it was pretty interesting to note that now you have weak lensing instead of X-ray to measure the mass. What's the discrepancy now? Can you predict what is the non-thermal or turbulent or support which you have for these clusters?
We don't directly have that. One thing, the only thing I can kind of tell you in a backward way is that if you look here at this AX parameter, the prediction for this parameter from in Viklin 2009, which is basically consistent with hydrostatic estimates, was 5.77. So this is basically here. So if you looked at the marginalized thing, it's, well, I don't know, it's hard to marginalize by eye, but you know, it's 1 point something sigma. So this is where we are with this. But with our data, we don't explicitly fit for a hydrostatic bias. There's plans maybe to do that. On the other hand, in terms of cosmology, we're basically agnostic to the value of what the hydrostatic bias is, and we just directly fit for the scaling relations.